Hello everyone. Welcome to Controllers Tech. This is another video in STM32 register-based series, and today we will be looking into DMA. DMA is a vast topic, and that's why I have decided to split it into few parts. Today we will cover the ADC in F446 with DMA, but without the interrupt. This DMA will be set up in the circular mode, and it will be always running in the background. And what better peripheral can we use here than the ADC? We can let the conversion to take place in the background, and whenever we need the value, we can just use it. This is not that simple in any other peripheral like UART, I2C, or anything else, where we need to process every data we get. So this is why I decided to go with ADC today. After this I will cover peripheral interrupt in the next video, and later I will combine them, and make a final video on DMA with interrupt. Today we will also see the internal temperature sensor. Let's start with Kyle ID then, and create a new project. I am using F446RE for this video. Select the CM/sys core, and the device startup files. Let's add the main file to this project. And create a main function, along with the while loop in it. Now the usual thing. We will copy the clock configuration, and the delay libraries. These libraries are covered in the previous videos, so watch them if you haven't. Add the libraries in the project also. Include them in the main file, so that we can use the functions here. We are done with our initial setup now. Since I am using ADC here, I will just use the code from my previous ADC video. This is the main file from that video, and we only need the initialization, enable, and start functions from here. Let me walk you through quickly. First of all, we enable the ADC, and the GPIO clocks. Since I am using PA1, and PA4 pins for ADC, I am enabling clock for the GPIOA. After that we set the prescaler for the ADC clock. We enable the scan mode, because we want to use the multiple channels here. Also the resolution is set to 12 bits. Then the setting for continuous conversion, etc. Next is the sampling time for the channel 1, and channel 4. Let's see the reference manual, because this will be useful for the temperature sensor also. Here the sample time register 2, can be used to set the sample time for channels 0 to 9. And register 1 can be used for the channels 10 to 18. Now since we are using channels 1 and 4, we are interested in these two sections. I will set the random time here, since the setting for these two channels don't matter. The sampling time will be useful, when we will do the temperature sensor later in the video. I am keeping the 3 cycles. So I need to write 000 in the 3rd position, and the 12th position. This can be done by writing 7, and then inverting it. Next is the number of channels, that we want to convert. This can be set up in the sequence register 1, and bits 20 to 23 configures it. If we write 0 here, that would mean that we want to convert one channel. So I am writing 1 in these bits, because I want to convert 2 channels for now. Then we are setting the analog mode for the pins. This was the setup from the previous code, now we will do some more addition here. You can read here in the manual about how to use ADC with DMA. Anyway, let's go to the registers. Here is our bit of interest. This is in the ADC control register 2. Bit 8 is the DMA, and we will enable it of course. Bit 9 is DDS, it basically specifies if we want the continuous DMA conversion or not. We will enable this one also. So let's enable the DMA for the ADC. Also enable the continuous request. Now we need to set the order for the channels. What I mean is, we need to set in what sequence the channels should be converted. Which conversion should happen first, and which should happen last. This can be done in the sequence register. These sequence registers can set the conversion sequence for up to 16 channels. This sequencing starts from the sequence register 3, and here you can see the sequence 1. That means which channel will be converted first. All we have to do here is, just write the channel number in the respective sequence. For sequence 1, and sequence 2, we have to modify bits starting at 0, and at 5. Here I am setting sequence 1 for channel 1. And sequence 2 for channel 4. This is it for the ADC modification. We will enable the ADC later. Here we don't need this anymore, since we are already using sequences for all the channels. Now let's initialize the DMA. F446 have 2 DMA, and combined they have 16 streams. DMA transfers can be peripheral to memory type, memory to peripheral, and memory to memory. Basically 3 things happens during the DMA transfer. Data is copied from the peripheral register, or from a memory location. Data is copied into the memory location, or into the peripheral register. And the counter decreases. This counter keeps the record of how much more data is needed to be copied. Here we have the DMA mapping requests. We can choose the stream based on what peripheral we are using. Since I am using ADC1, have to choose stream 0, and channel 0 of DMA2. We are definitely going to use the circular mode here, and as you can see, in the circular mode, the counter value gets updated on its own. So the data transfer continues forever. Let's see the registers. First we have the lower interrupt status register. It's called lower because it can handle the stream 0 to stream 3. This register will be used when we will include the interrupt with DMA, which we are not doing today. Then high interrupt status register handles the streams 4 to 7. Interrupt flag clear registers are used to clear those interrupt flags set in the interrupt status registers. Now we have reached the stream configuration register. But before that, let's enable the DMA2 clock. It's the bit 22 in the RCCA HB1 enable register. Now we will configure the stream. Let's start from the least significant bit. Bit 0 enables the stream. We will do this in the end. We are not using interrupts, so these bits are of no use. Here, the fifth bit is peripheral flow controller. We want the DMA to control things, so we will keep it 0. Then we have to select the direction of the data. We are copying the data from ADC to the memory, so the direction will be peripheral to memory. Next is the circular mode, and we will enable it. Let's set these things first. We will set the data direction. DMA stream 0, and in the control register, we will set 0, 0 in the 6th and the 7th positions. Circular bit is bit 8. Set the circular mode for the DMA. Then we have peripheral increment. We will not increment the peripheral address, as we are copying the data from the data register only. And yes, we do want to increment the memory address after each transfer. This way the buffer will automatically increment, and the next data will be saved in new location. So write a 1 in the 10th position. Next is the peripheral data size. As I am using 12-bit ADC, I need to use 16-bit data size here. And the same for the memory data size also. So we will write a 1 in the 11th position, and the 13th position. Then we don't need all these bits for now. At last we have the channel selection. If you remember, I am using channel 0 for the DMA. And that's why I need to write 0 in the 25th position. This is it for the DMA initialization. Now we will configure this DMA. This function will take three parameters: the source address, the destination address, and the size of the data. This should be 16-bit here. Let's see the reference manual again. Next register is the NDTR. This is a 16-bit register, and here we set the size of the data that needs to be transferred through the DMA. If you remember, in the beginning, we saw that after each transfer, the value here will decrease, and once it reaches 0, the DMA transfer will stop. Also, we can only update this if the stream is disabled, and that's why we haven't enabled the DMA yet. Let's set the size in the NDTR register. Next in line is the peripheral address register. Here we write the address of the peripheral register, where we want to copy the data from, or copy the data into. In this case, we are copying the data from the ADC into the memory, so the peripheral address will be the source address. Similarly, there is memory address, where we are copying the data into, and in this case, it's the destination address. If you notice here, we have two different memory address registers. But this one can only be used in the double buffer mode, and that's why we are not using it today. So that's all for the DMA configuration. Now finally we will enable the DMA by setting the bit 0 of the control register. This finishes up the DMA configuration. Now let's define an array to store the two ADC values. In the main function, we will start with system clock configuration. Configure the timer for the delay purpose. Initialize the ADC, and initialize the DMA. Now we will call the DMA configuration function. First we need the source address. The source is the data register of the ADC1, where we are copying the data from. Destination is the array that we created. And we want to transfer two values. I should have enabled the ADC after the initialization. And now after everything is set, we will start the ADC, to start the DMA transfer. Okay, everything looks set, so build it. We have 0 errors, so let's go ahead. The controller is running at 180 MHz. Let's debug it now. I am adding the RX data to the watch expression. Let's run it now. I need to change this data type here. Okay, so I have connected the channel 1 to ground, and channel 4 to the 3.3 volts. The readings are as expected. And now I have connected the channel 4 to ground, and channel 1 to the 3.3 volts. So the things works pretty well. The DMA will keep getting the data from the ADC in the background, and this data will be stored in the buffer. We can use the buffer at any point in the code, and there we will always have the latest values to process. This you will see in a while, when we will do the temperature sensor. I want to show you guys one more thing. Let's put a breakpoint here. We are at the breakpoint now. Pay attention, the DMA is already enabled, and also the ADC, but the values are not updating. This is because I haven't started the ADC yet. And now the moment we start the ADC, the values will be stored. This is something useful in ADC, since it have a feature to control the start condition. But if we are using something like UART, we don't have any start condition in that. And in that case, as soon as you enable the DMA, the data transfer will start. To debug your code, you can look at the DMA peripheral. As I am using stream 0, only S0 registers will be relevant. You can see the NDTR is 1, and if we step over, its value decreases. Since we are using circular mode, this value will not reach 0 of course. This is it about this part. Now we will see the internal temperature sensor. This will be a kind of application of the DMA. Let's see the datasheet again, and this time we will look for the temperature sensor. It is channel 18 of the ADC. Here are the steps to use the temperature sensor. We need to enable the channel 18. Then configure the sampling time for the channel, and it should be higher than the one specified in the datasheet. Then we have to set this TSVREFE bit, to wake the sensor. The rest of these steps are already taken care of. So we need to only focus on these. Remember the sequence register, we have already set the sequence of the two ADC channels. Now we will set the sequence for the channel number 18, that is the temperature sensor. Basically we just have to write the channel number to this 10th bit. So we will write the 18, in the 10th position. Now the sampling time. As given in the datasheet, the minimum time needs to be 10 microseconds. So we must select the conversion time higher than this. Also note that the ADC1 is connected to the APB2 clock, and since my setup runs at maximum clock, the APB clock is also running at 90 MHz. I wrote one article about calculating the frequency, and the conversion time for the ADC. Here is that formula, and we will use this one. Also note that the sampling time we can choose is limited to these values. In my setup, I have used the prescaler of 4, to divide the APB2 clock. This will bring it down to 22.5 MHz. Now if I choose the 144 cycles, the conversion time comes around 7 microseconds. This is less than the value in the datasheet. For 480 cycles, it comes around 22 microseconds. This is way higher than the datasheet value, but I guess we can work with it. You should modify the prescaler also, to keep the time close to the value in the datasheet. We need to write 7 in the 24th position here, since we are setting it for channel 18. Now we need to set this bit in the CCR register. Here it is, the bit number 23. So let's write 1 in the 23rd position. We just need to do one last thing. The number of conversions was set to 2, and we will change it to 3 now. Let's copy the formula from the datasheet. Here V sense is the voltage, corresponding to the ADC value. V25 is given in the datasheet, and it's 0.76. We are receiving 3 values now. Average slope is 2.5 mV per degree Celsius. Change it to volts. Let's define the temperature variable. We have a warning. Anyway, let's move on and debug this. You can see the temperature is around 36 degrees. I wouldn't call it perfect, but this is close. It should be around 33, or 34. This could be due to the conversion time I took, because it was more than double of that in the datasheet. That's why I said that you should also modify the ADC prescaler also, and try to keep the conversion time close to that value. Anyway, you can see the ADC values from all 3 channels are updating. The last value is for the temperature sensor, because we have set the sequence 3 for it. So it will be converted and stored in the 3rd place. This is it for the DMA. I hope things were clear. There are minor changes in the F103 controller, and I think you can handle them, if you have watched the video properly. If you want me to cover the UART DMA in F103, leave the comments below. This was the circular mode, so the DMA will keep running in the background, without affecting the CPU. I will also include the non-circular mode settings in the final code. There you can just call the DMA whenever you need, and after all the conversion is finished, it will stop automatically. Check the final code for that. This is it for now. Leave comments in case of any doubt. You can download the code from the link in the description. Keep watching, and have a nice day ahead.